Now we introduce a deeper visual motor policy for robots. The goal for the policy search method is to learn a control policy, pi, based on observation. We select optimal action U. That means we, for agent, need to select action at a time t according to the observation to control the system dynamic. For example, we have a policy, and for initial state, we have to select a proper action, because environment is dynamic, is unknown. So we have to carefully select action U, make sure robot can move from initial state S to next state S prime, and so on until we reach the terminal state. That means we need a policy. Let me say, use the policy search method. We need to find a policy on a trajectory, not just a single policy, because a single policy, if we have a small error, can cause a problem in a later time. So right now, we need a policy along the trajectory, means we have to find a policy distribution along the trajectory, make sure we can start from the initial state, finally we get the correct terminal state. So the policy on the trajectory is defined as you see in the time series. First, start from T1, we have a false state here. We select the action. Based on this action, we control, what's the system dynamic. We still use the expectation loss along the trajectory, and make sure when convergence, we get the learned policy has the same distribution as the system controller P. Deep visual motor policy is a end-to-end method, which now the deep visual motor policy method include or use two major steps to solve the policy search problem. For example, the first one is trajectory-centric reinforcement learning. That means we have we use the controller generate trajectory, but we have observed trajectory. This should be same if we know exactly the system dynamic. But then, however, we cannot get the accurate system dynamic. That means the two trajectories have a difference. We use this difference to improve the system controller, make sure these two trajectories are close, as close as possible. And then we use this system controller as a target to train our policy. The policy training, we use a supervised method. We use the system controller as a target to train the policy. We assume the policy is a Gaussian distribution. That means we can express the policy as a Gaussian distribution. That means we have a mean and covariance. We train the policy, we get the optimal mean and the policy and the covariance. That's the idea. And we can, from this figure here, we run system controller, get the trajectory, and we pre-train the policy network. And then we use the trajectories, difference between the two trajectories to improve the controller, and use the controller as the target to train the policy to match the controller P. One thing, we got the convergence result status. Then now we can, we can make sure the policy we learned is match the controller P. We can use this figure to describe the deep visual meter policy. For example, this is the RGB image. This is from a robot camera, and then which used as the input of the policy network. Then we get the feature map. From this feature map, we get the features list. Because the policies depend on the observation and the robot state together, we get the full state features. We cascade the observation features and the robot states together as the input of the next 3 or 4 connected layers. Finally, we output the actions to control the robot. Because this deep visual motor policy method, this end-to-end training method, we have to combine the two parts into one procedure. From the observation input, we get we got the output of the policy. We use, we convert the original constraint problem to the Lagrangian problem, and then we use the gradient descent method to solve the problem in the primitive space and do space. The original problem is to find the policy pi by solving a constant problem. This minimum problem. This is the expectation loss, and make sure the policy we learned is equal to the system controller. And this constraint problem above can be formed as a Lagrangian, solved by using gradient descent method. Then we solve in both space. Use gradient descent method. The Bregman alternating direction method of multiplayers have the following Lagrangian formulation with regard to the parameters theta is related to the policy network, and the P is the system controller. Then we have we got 2 objective functions. It's one for policy optimization, and the second one is for the trajectory optimization. At the convergence, then the policy we learned has the same distribution as the system controller. That means then we can use this pi to run the as a model to policy to run the robot, and can get from initial state can correctly reach the terminal state. Even the case is never seen in the training data set. Okay, if you need more information, please check these references. Thank you. Bye.